Today I'm going to talk to you about how we evolved the DHCP infrastructure at Facebook and brought it to 2015. A little bit about myself. I joined Facebook in 2011. My team was called Site Reliability Operations. Oh God, there was a lot of firefighting there. We spent 2 years automating ourselves out of the job. After that, the team was basically closed. People moved to different teams. I moved to a team called Cluster Infrastructure. Cluster Infrastructure is basically responsible for core services. So all those basic services that are needed to run data centers. So things like DHCP, TFTP, DNS. And we also own some components that are used for the provisioning toolings we use to install operating system on the actual physical boxes. We do other stuff. We do stuff like fire drilling, clusters in data centers. We also brought toolings to help with turning up clusters in data center in an automated way. Yeah, so that's what we do. So today, my talk is specifically about how we made DHCP better. So I'm going to give a small overview of how clusters are laid out in terms of the network. Then we're going to talk about why we use DHCP and how we use it, and some of the limitations of the old architecture and how we solve those problems. And at the end, some lessons learned and takeaways that I hope you guys can take home as well. So yesterday was a talk about data centers, so I'm not going to talk a lot about this. This is a picture from Luleå, a bunch of racks here. So you all know a bunch of racks, machines stacked, and on top of each rack there is a rack switch. We are in the process of migrating all the infrastructure to Wedge, as you heard yesterday, or previously seen it yesterday at the reception. But we have many racks, right? 100 of them in any single cluster. They are all connected to a bunch of cluster switches, typically 4, and in turn they are connected to the data center routers and to the rest of the network. Each single rack has its own /24 or /64 network, so it's basically a layer 3 net. Every cluster is a separated layer 3 networks. So let's talk about why we use DHCP, basically for two main reasons. The first one is providing network configuration to bare metal machines that are booting up so that they can basically install the operating system on the box and then start the whole installation phase. So we basically just do DHCP at the reboot phase. After the operating system is installed, we just run chef cookbooks and we configure the IPs statically. The other reason we use DHCP is for configuring out-of-band management consoles. So we assign IPs to them, and they typically renew their releases between 24 hours and 38 hours. So there's not much basically traffic on the DHCP side, but there's a lot of automation. This is a diagram of the Anyshake. I know everybody knows about it. What we really need to to be pointed out here is that because every rack switch is a separate network, we need a relayer that can intercept the broadcast discovery packets and basically encapsulate them into a unicast packet to the different DHCP servers in the infrastructure. We also do DHCP v6. As you might already know, we are almost exclusively turning up clusters in single stack v6 only mode since June or August last summer. So we need to support v6 also for DHCP. It's similar in terms of the 4-way and shake, and there are some similarities, but no option name is different. The format of each option is different. The thing to keep in mind is that DHCP v6 does not provide routing information. It doesn't give you a default gateway. Why is that? Because that is provided by the IPv6 routers in the network via special packets called router advertisement packets. And the other difference is that there is no broadcast before address, of course, but you have to use a special multicast IP, which is the one there in the slide. Last difference is that V4 used the concept of MAC address to identify a client In V6, there are different ways of doing that, but we chose to use the way called DOID-LL because it's basically embedding the MAC address in it, and we can just extract that MAC address and use it to basically pinpoint the information into our inventory system. So to go back to the previous picture, this is basically the same picture as before, but you can see that in every rack switch there is a relayer, which is basically just an agent running on the rack switch that you can configure to say intercept all the broadcast packets and send them to the DHCP server. We used to have 2 DHCP servers per cluster. We are migrating into containers and having like regional DHCP servers right now. This is what we're working on. So let's talk about the problems we had before. In the past, we had hardware load balancers, and we were configuring an internal VIP, and behind this VIP, we had basically 2 DHCP servers. One was active, was taking all the traffic. The other one was standby. It was based on the standard ISC DHCP daemon, and we were pushing configuration to those servers. The problem was something like bot goes down, no DHCP in the cluster, you can't repair or provision boxes in that cluster. So this was some problem. We didn't want that. The next problem was bootstrapping clusters. Bootstrapping is the process of borrowing core services from the closest clusters in the same data center to basically provision operating systems on that cluster. We used to have DHCP servers that we called routable DHCP servers, which are basically the same as the cluster ones, but the difference is we used to ship configuration for all the MAC addresses in that given data center. So as I said before, we have relayers on rack switches. When you were bootstrapping the cluster, you needed to take every single rack switch, go into each one of them, change the DHCP helper, the relayers to point them to the IP of the routable DHCP server. That was not done manually, obviously. We had our own automation in Python to do that. And we hooked that into our cluster to not provision into. But I wasn't very happy with that. I just wanted things to work transparently. Here's another problem. Configuration distribution. There was a talk yesterday about pipelines, so pipelines can break, a lot of steps. We had basically a 15-minute cron job, fetching all the MAC addresses from the inventory system for the whole fleet, writing down the ISC, DHCPD configuration files, so like subnets, X, all the machines in there, next subnet, all the machines in there. Write them all in a temporary file, then push them into the Git repo. Then, propagation times, the master repo was propagated to different regions. Then we had Chef automation to bring those files into the cookbooks, and then Chef was running every 15 minutes every machine in every DHCP server to fetch those files, put them into EDC, DHCPD, change the whatever configuration part needed to be changed, and restart the server. This is fine. I mean, it was working fine, but there are a lot of people in the data centers changing hardware all the time. A mainboard breaks, an hard drive breaks, a network card needs to be replaced. So these people go around and they change those cards. When they do that, they need to change the MAC address in the inventory system. And because of that pipeline I mentioned before, and the amount of swaps that happens all the time, sometimes it was taking 4 hours for a single MAC address change to propagate down to the DHCP servers. So those people were not very happy about it. So the other thing was that because of all the changes happening and machines being added, subnets being removed and stuff, the DHCP server was spending a lot of time restarting rather than actually serving traffic. Another problem, lack of instrumentation. We didn't have any of this. We didn't know how many RPS we were doing. We didn't know what were the latencies the clients were seeing, how many errors, exceptions we were doing. We were basically flying blind, and production engineers don't want that. They want to know when stuff are broken. They want to know which client is misbehaving and if there is a problem in the network and such. So we sat down, we spoke about it, like we wanted to see where we could improve things, and so we wanted to support V4 and V6. We wanted the stateless server. For stateless, I mean that you shouldn't need to ship configuration with the application when you are deploying it. So your application should be able to pull all the data it needs from an external endpoint, in this case, the inventory system. We wanted to get rid of the hardware load balancing. At that time, we were in the process of basically replacing all the hardware load balancers with software load balancers. And we wanted something that was easy to put into our container infrastructure, which is based on Linux containers. So basically, we wanted it to be integrated with the infrastructure. Sorry, I need to take some water. So I spent 4 weeks, maybe more, looking at things I could reuse because I didn't want to reinvent the wheel and write something from scratch. So I looked at different projects, but at the end I just happened to have a look at this project, ISC Kia. It's a project from the Internet Software Consortium, the same people that develop DHCPD. They decided to rewrite DHCP from scratch. They started in 2009 with a very bad name, like bind10, why would you do that? And I think at the beginning of 2011, they started writing the DHCP component. But why did they do that? I mean, DHCPD is stable, right? Yeah, but it's like 20 years old piece of code, It's not built like for 2015. It's basically monolithic, mono-threaded C code that is complex, not modular. It's not really easy to extend. And their open source model was really not open source. You couldn't get the code base in GitHub. It wasn't ready for 2015, and the backtracking was semi-closed. And it was lacking for performances. So they rewrote. This is a diagram showing how it's done. The base layer is a C++ library called libDHCP++, which is basically a general purpose library to parse and assemble DHCP packets in V4 and V6. There is support for interface detection, socket management, so basically whatever you need to write the proper UDP server and start receiving traffic. And the configuration file is no longer like a file with its own DSL. It's just normal JSON. You can use Chef to produce it and stuff. But what I really liked about Kia was that they provide this API. They call it the hook API. It's basically an API that allows you to hook your logic into different phases of the receival of a packet. So these are some of the phases, like receiving a packet, selecting a subnet, selecting a list, and sending the packet. At each one of these steps, you can inject your logic. So what you need to do is basically write your own C++ shared object and configure the application this way to have the application dynamically loading the library within the binary. So this is an example of a file, a configuration file, pretty easy, just logging, configuration, the path of the library there, the interface you need to listen on, some of the default DHCP options. But there's something strange in here, isn't it? Like subnet, what is that? This is the whole V4 space of the internet. Why did I need to do that? The reason I needed to do that was that at the time I started using this project, they didn't have host selection. You couldn't say, this is the MAC address, this is the gateway, this is the other MAC address, this is the gateway. They were only supported dynamic allocation. But I didn't need that. But I really wanted to use the API, so I said, okay, let's configure the whole V4 space. I don't care when the packet is going to leave the interface. I'm going to just override whatever it's in there with my IP address that I want. So this is a small diagram that shows the life of a packet as it ingresses the DHCP server. There it is. Goes into Kia. Kia does some initial processing, verify that the format of the packet is correct, or some of the mandatory options are in there. Then it takes this and it stores it into a context object. Context objects are basically like long-lived object that lives for the duration of this four-way handshake. So for the duration of this four-way handshake, you have this object. Because your send and receive hook will be called twice. Once when you get the first request, then you send the acknowledgement, then you get the second request. So you're going to be executed twice. So you need something that stays in memory for the duration of this handshake. So this is stored there. Then my receive function is called. I get the information from memory. Here's where I do the actual calls to the inventory system, like, hey, this is the MAC address. What is the IP? What is the subnet? What are the PXE options I need to use if I need to? Doing some logging, like alerting and stuff. So I get this back. So when I started doing this, I didn't have any cache, and I broke the inventory system. So then I put some in-memory cache there. So once I get this information, I store them back into the context object. Then I skip those phases because, as I said before, we don't do dynamic allocation. We just know already what IPs are assigned to which MAC address. So we skip those phases. Then what I get is basically an almost empty outgoing packet. And this is where I get all the information again, and I store them into the outgoing packet. Then I just do some logging, sending them to Kia, and then the packet finally gets back to the client. Some code, yay. This is an example, very basic example of our API, really simplified. You need to define all of these functions. Like in the load function, you just allocate whatever objects you're going to need for the duration of your daemon, and you unload them in the load function. Then this is basically the core, right? In the receive part, you can just use the handle object to get the incoming query for packet, and you get back an object, which exposes a lot of methods to extract all the options you need from the packet. In this case, I need the MAC address. There it is. Then this is some pseudocode to simulate me making a call to the internal system, get host info. I pass the MAC address, and I get back. I pass a pointer to a reference to the host info object, and I get that filled up. And then I do some logging, and I get this host info object, and I set that into the context, which is basically which lives for the duration of the handshake. Then on the send part, I just get the pre-compiled, like pre-assembled version of the outgoing packet from that Kia gives me. Then I get the object that I stored before. I fill up all the relevant information that I need taken from the inventory system. Then I log some stuff and just exit from the function. So supposing you have Kia installed in your box, this is how you can compile it. You get back this child object that you can put somewhere you want, and then you put the path in the configuration file. So this saved that made the things so much better. We don't have any more static configuration coming with shipped with the DHCP daemon because everything is pulled from the inventory system dynamically. The people in the data centers are much happier because there's no more need to wait 4 hours. Everything is propagated maximum in 5 minutes because of the TTL in the memory cache on the DHCP server. So that makes deployment easier. Just take a binary, generate the JSON file, which is almost identical everywhere around the fleet, and just ship the binary. That's it. And some of the configuration is integrated to our configuration management system, which is based on Python DSL. And, no more hardware load balancing. We got rid of them. We now use Anycast ECMP. So Anycast basically allows you to send the packet, and the packet arrives to the closest service in topological terms. So we set up a global Anycast IP, which is everywhere across the fleet, and it's assigned to every DHCP server across the fleet. And we use a small Python open source daemon called XABGP to advertise those routes, the rack switches. So that means that basically the DHCP server just becomes routers effectively, and they just join the infrastructure with the other network routers. Diagram showing how this is done. Bunch of DHCP servers in one region, other DHCP server in another region. They have different IPs in the ATH0 interface. We configure 2.0 interfaces with the Anycast IPs, and then we just talk to XABGP, and XABGP advertises those routes up to the top of rack switch that advertise everything back to the infrastructure routers. So ICMP basically allows you to choose a path. In this case, for example, we have a client, which is a rack switch relayer in one region. So the protocol basically picks a path which has the least cost. In this case, one of the two paths there. But if you have the same distance, there's a sharding algorithm that basically chooses one of them and sticks with that box. When both goes down, the next distance is picked, and it behaves basically the same way. If the distance between the two is the same, one of them will be picked, and you're going to stick with that. Here's what really improved turnups. Because the NGAS IP is unique, we just configure the same IP everywhere, and we don't have to run this horrible Python script anymore. We got rid of a bunch of logic in our automation tool to do turnups. Basically, everything is transparent now. We could almost get rid of the routable DHCP servers, but we want to keep them in case of like very bad failure scenarios where all the DHCP servers are down. So this is no longer needed. And we have metrics now. This is a nice dashboard that I have. I watch like sometimes. I have alarms for them. We can have this now because everything is logged by the application itself. And now it's time for war stories because I know we all like them. So last June, we were in the process of tuning up our first ever V6 only cluster in Luleå. But it wasn't so simple. We found a bug in the BIOSes. We couldn't fetch PXE seeds via TFTP v6 when both clients and servers were in different VLANs. Okay, damn it, we are doomed. So we checked with the vendors, and they told us that they would have spent like months giving us a fix. But we were running out of capacity. We want to, if we are bringing up stuff, it's because we know that soon we're going to be out of bandwidth. We need process capacity and stuff. So we went and we did the workaround in pure SRE style, right? I was talking to people like, we are doomed. How are we going to do it? And someone told me, you can run Python scripts on rack switches. You know that, right? At the time, we didn't have Wedge. We had vendor proprietary hardware. So you could run very small Python scripts there. Let's write a very quick and dirty Python TFTP relayers that just listen on an interface and relays all the UDP packets to a single IP that you can configure. Okay, next we are going to deploy this everywhere in the cluster. And then because I own the DHCP code base, I can do whatever I want with the outgoing packets. Let's just overwrite the default TFTP IP with the IP of the rack switch for that given box, so that we were basically using the rack switch as routers for TFTP packets. So we did that, everything went fine. We were able to deploy it, and we got the fix a few months later from the vendors. And because it takes time to roll this everywhere, we are still rolling out the fix around in the field. So time for some takeaways, at least for me. Design your service in a stateless way. Try to do that because it's good. So that means try to keep the status away from the actual application. Put it somewhere. Someone else will take care of the state of your application, and that simplifies configuration, of course, and the deployment. The other takeaway I have is try to balance the not invented here syndrome. Try to reuse software as much as you can, and only really write stuff from scratch if you really need it. For example, for FBOSS, we didn't have an alternative, so we decided to write it from scratch. So here's what I had to talk about. There are some pointers to Kia if you want to take a look and you want to use it in your infrastructure. Here's XBGP that we use and some links about FBOSS. Any questions? We have 4 minutes, so you can just shoot questions to me.
How angry? Am I on? All right. How angry was the team that runs your infrastructure? Your inventory database when you told them that you'd be querying it every?
They were cool. They just put me they just contacted me on ISG and said, "Hey man, what the fuck are you doing?" I was like, I'm just making some queries. But really, yeah, I had a hard conversation with them. We just talked about it, and they offered like. So the problem was also not only that I was doing a lot of queries, more than they were expecting, but also that their API wasn't good, and I was making 3 calls when I wanted really, I could just make 1. So I stopped. Basically, I stopped my experiment, and I gave them time to rewrite to give me just another API method to do what I wanted with 1 call. So I waited them to do that, and then after they were done, I just started to use that, and I did the cache. So yeah, they were cool. I mean there was not much like, bitching about it.
Cool.
Yeah.
And do you like warm up the cache in advance, sort of pre-populate everything, or is it just on demand every time?
No, I don't do that. It's just very simple, like TTL-based cache. So if I restart the server everywhere, of course, they're gonna be hit more, but we don't just restart everything everywhere. We just do like slow rolls, so we upgrade packets very slowly. So, yeah. Cool. Thanks.
So have you tried load testing? Any idea how many machines you can install at the same time or boot in a cluster?
Yeah, so we did that. We did like a full cluster provisioning, and we found some bottlenecks, but they are not in DHCP. They are in some other endpoints, which is not the inventory system. It's another endpoint that we actually happen to own as well. So yeah, we are working on making that faster. Yes. So we did some load tests. So because this is provisioning and we have automation, you can just fire a job and say, hey, install OS on X thousands box, and then you just send me an SMS when it's done. So even if it's very slow, you can just go to sleep, and it's gonna get done like in 3 hours, 4 hours, or something. So it could be better, but it's not high priority to be that fast for us at least. Cool.
Do you using Anycast to spread the traffic across hosts? Do you find that you get much? Do you get good load distribution, or do you have to start picking where your hosts are going to be in the network in order for that to work smoothly? Or
so we are going towards a regional model where we have like a bunch of servers per region. For region, I mean like basically the same data center at the moment. So no, I didn't really think about that, but I haven't actually looked at to see if the load is evenly distributed. Like, to be honest, I can't say. I don't want to lie, so yeah. Fair. I'm gonna look tomorrow probably in the dashboard and see if it's true. But yeah. Thanks.